Hey guys, Physics in the Flesh is back with another conservation of mechanical energy problem. A projectile is fired at an upward angle of 45.0 degrees from the top of a 256 meter cliff with a speed of 158 meters per second. What will be its speed when it strikes the ground below? So this kind of question we actually encountered earlier in kinematics and dynamics, where we dealt with speed, vectors, components, x and y. Now, the beautiful thing about energy and work is that you don't need to use components anymore. But you know what? I'm getting a bit ahead of myself. Let's just start off the problem with drawing a picture. Okay, and my picture is going to be super simple. There's my cliff. Okay, and there's a projectile on top. It's getting fired at an angle of 45 degrees. So that's 45 degrees. Of course, it's going to go up. It's going to reach its maximum point. It comes back down. And our task is to find its speed when it reaches this point right here. Okay, so getting back to what I said earlier, the beautiful thing about energy and work problems is that energy is a quantity that is a scalar. Okay, in other words, it has no direction, it only has a magnitude to it. Okay, so you don't even need to worry about things like it's fired at 45 degrees. It could have been fired at 67 degrees, 23 degrees. The point is, you know the speed. Okay, we don't need to have vectors when we're dealing with energy, and we're going to use conservation of energy to solve this. The reason we can do that is because we have enough information. Okay, so at this point right here, we can call this point 1. We know the height of the object. We'll call that h1. It's the height of the cliff, 256 meters. We also know the speed. It's 158, so v1 is 158 meters per second. And what we're looking for is the part down here, so we'll call that instance 2. Okay, now we know that here the height is 0, h2 equals 0 meters, and we are tasked with finding v2. So you see, the problem became as simple as that. Even if the problem asked you at any other point in its path what the speed would be, or if they gave you the speed and they wanted you to figure out the height, you just pick any point along the path and you use conservation of energy. It's that simple. Okay, so let's do our ET1 equals ET2. And the two types of energy we're dealing with here are gravitational potential and kinetic. So my ET1 is going to be replaced with EG1 plus EK1 equals EG2 plus EK2. Okay, so now replace them with what they're represented by. So mgh1 plus 1/2 mv1 squared equals mgh2 plus 1/2 mv2 squared. So we've got this really long expression, but if you've been watching the past couple of videos, 107, 106, you would have seen that this is going to simplify a great deal. Okay, so for example, the first thing is that mass appears in every single term. And because of that, imagine factoring it out. If you factor it out to the front, it'll be divided out of both sides, resulting with no mass in any expression. The idea is this: if you have something that appears in every single term, you can cancel it out, especially when there's a plus or minus in between them. Okay, so mass disappears, which is fine because we weren't given one. Some other information we know that h2 is 0. So if that's 0, this whole expression becomes 0 because 0 times anything is 0. So that just disappears. So let's rewrite what we have left. We have gh1 plus 1/2 v1 squared equals 1/2 v2 squared. So although this expression isn't as easy as the ones in videos 107, 106, we can still plug this in and solve it, right? And all we're looking for here is v2. Okay, so I'm just going to go ahead and plug my stuff in. Okay, so 9.8 meters per second squared. h1 is 256 meters plus 1/2 v1 squared. v1 is 158. So you see, you don't have to do components or anything. You just plug it in as is. Equals 1/2 v2 squared. Okay, so I'm going to just solve this first, then I'll multiply both sides by 2 to get the v2 squared by itself. Okay, so the left side of this expression, if you calculate it, you're going to get 14,990.8. That's going to be meters squared per second squared equals 1/2 v2 squared. Okay, so now you want to multiply both sides by 2 and take the square root. Okay, so if you multiply both sides by 2, you're going to get 29,981.6 meters squared per second squared. And if you want that to be equal to just v2, right? So right now that's equal to v2 squared. Take the square root of both sides. That'll cancel the square there. And so you're just going to be solving for V2 now. So square root this big number and you will end up with V2 equals 173 meters per second, which is accurate to the correct number of sig figs, which is 3. So that is the answer to this problem. I hope you guys saw how simple that was. All you need is conservation of energy, no components, super simple. So guys, if you like this video, be sure to smash that like button and subscribe to Physics in the Flash so you never miss another video from me. Check out video 109 that'll get posted next day at 12 noon. Conservation of Mechanical Energy 3. Hey guys, welcome to the end screen. Woo, I got you guys. All right, here's what I need you to do. Subscribe to this channel. Okay, I'll stop. Thank you guys so much, as usual, for watching. If you guys enjoyed this video, be sure to subscribe to my channel by pressing the red subscribe button below and smash that like button so that I know what I'm doing makes sense to you guys. First face reveal I do and my hair is all frizzy. I post new videos every weekday at 12 noon. Finally guys, I love you so much for watching. Please continue to do so every weekday at 12 noon.